This is Thermodynamics video 16 about excess properties and activity coefficients. In general, we have an excess property defined as a property minus the ideal property, and ID is ideal liquid. One simple way to state that liquid is ideal is that it obeys Raoult's law. The partial molar excess property of a component is the partial molar property of component I minus the partial molar property of ideal liquid. That is equation 1189. And we can perform a deduction equal to the one for residual properties that is similar to ideal gas and residual equation. We have the change in excess gives free energy over RT is MVE over RT dP minus NHD over RT squared dt. And then we have to add for the possibility to have a change in all the components. And the proportionality factor is the partial molar excess gives energy over RT dNI. And then we have a similar way to introduce the activity coefficient. The activity coefficient is actually defined by the fugacity over the liquid mole fraction times the pure component fugacity. That is a theoretical or thermodynamic way to define the activity coefficient, and that is linked to that. Actually, I prefer to look at the activity coefficient as a correction factor in the ideal liquid description. Then I must admit that also here there is some different symbols used in the textbook. Then in the textbook they use the activity coefficient as a fugacity coefficient for a pure component divided. So this is the way they do it in the textbook, but the way I do it, that is the normal way in most textbooks. I prefer to use the activity coefficient in mixture with that symbol. In the textbook they have this hat on a mixture property, and this is the mixture fugacity, and I put a pure on the symbol for a pure component fugacity. And this is a little different in the textbook. Then I put up GT over RT equals the sum of xi times ln to the activity coefficients This is for constant pressure and temperature. If we take this equation and say that the pressure is constant, the temperature is constant, then we avoid these two, and then we end up with just a connection of the excess Gibbs energy and the logarithms to the activity coefficient, and if we divide by the amount, the m, then we get the mole fractions. So then we have this equation, and this is used to correlate activity coefficient models which describe liquid non-ideality as a function of composition. If we have some excess Gibbs free energy or we have some non-ideality, that will normally vary with the composition, that is the mole fractions of the liquid. And if we have a model to describe this non-ideality, then this can be correlated into this equation. We will come to that in chapter 12. An ideal liquid I have just stated here that ID is ideal liquid, but I have not defined actually what is an ideal liquid. But I will just state a few things that is typical for ideal liquids. An ideal liquid follows Raoult's law. That is, the partial pressure is the saturation pressure of a component times the mole fraction in the liquid. Volume is the sum of the volume for the pure components times the mole fraction. So if you mix ideal liquids, or if there is an ideal mixture, then the volume is the sum of the volume of the liquids you add, and the enthalpy is the sum of the enthalpy for the pure components times the mole fractions. And G excess and the activity coefficients are measures of non-ideal liquid. If GE is 0 or the activity coefficient is 1, then we talk about ideal liquids. Then I go on, and this is still from 11.9. The change in excess gives energy over RT is NVE over RT dP minus NHE over RT squared times dt plus the sum of ln gamma dNi. This is 1193. This means that ln gamma is the change in NGE over RT dNi when we keep pressure, temperature, and all other components constant. And this is the partial molar property of GE over RT. The first part can be found directly from 1193, and because we have a definition of a partial molar property as the derivative of the property by the amount of the component when pressure, temperature, and all components are constant. And then that is the partial molar property of GE over RT. Or that is ln to gamma is a partial molar property. And I have tried to explain that a partial molar property have some properties that are useful. So mGe over RT is the sum of Ni times ln I, and we divide by n to get GE over RT equals the sum of Xi ln gamma. That is 1199. And we have the Gibbs-Duhem equation for ln gamma, which state that the sum of Xi times G ln gamma equals to 0. We will also come back to this. I just put it up here. That it is at constant pressure and temperature, and it is equation 11,100. Perhaps they have too many equations in that chapter. But in this video, I have tried to put up some of the important equations for ideal and non-ideal liquid. We define the excess property as the difference between the property and the ideal property. That is also valid for a partial molar property. And then we can deduce a general equation that is always valid for the Gibbs free energy excess over RT. If we define the activity coefficient, we can replace the last part of this equation with the sum of ln of the activity coefficients times the amount of added component. And then if we have constant pressure and temperature, we have quite small compact equations, and these can be used to correlate the activity coefficient to liquid non-ideality. And I have given some properties of ideal liquid to explain what that is. And then we can define ln gamma as a partial molar property. This can be shown by this equation. And we have other connections like the Gibbs we have equation which states how the liquid activity coefficient is varying with the composition at constant pressure and temperature. That is the end of video 16. This is video 15 in the Thermodynamics course with LarsErik, and we are in subchapter 11.6 in the textbook, and the topic is the fundamental residual property relation. I start with a closed system. And I hope this one should be familiar to you. It's the relation between Gibbs free energy and volume, pressure, entropy, and temperature. This is equation 6.6. And if we divide this by RT, we get dmg over RT equals nV over RT dP minus nh over RT squared. This is 637. There is some manipulation to get from here to there. About 31 equations in chapter 6. But this is also a traditional equation when it comes to change of Gibbs free energy with pressure and temperature, and this equation is dimensionless. Ng is energy and RT is energy. For an open system, we have started with a closed system. We only change pressure and temperature. Now we are going to change the amount of each component. This is the same as fix 37, but now we also add some components, and when we add some components, then we must multiply with the partial molar Gibbs free energy, and we have divided all the equation with RT. And this is 11.4. This equation 11.54 is general. This equation just states this one, which is also general, and we just add more amount of each component, and then this is the proportionality factor when we are adding more components. because it is general, it must be valid for ideal gas. So dmg over RT equals nVIG. I just put superscript IG on all the properties. And again, we sum up the ideal gas partial molar property. And if we now want an equation for the differential of the residual gives the energy over RT, that is the difference. A residual property is the difference between the actual property and the ideal gas property. And here we have one general equation for a property, and this is the equation for the case of ideal gas. So for a residual property, it should be the difference between that one and that one. And when I'm writing, I'm just changing the superscripts. So then we end up with 1155, and we can do the same, and then just replace this with an expression for the fugacity coefficient. The fugacity coefficient is directly related to the partial molar residual property, like this. And then we have 1156. And as a result of this, and these are theoretical equations, and we are manipulating them, but I am after a result that we can make use of. and the logarithm to the fugacity coefficient can then be the partial derivative of mgr over rt by the amount when we keep pressure, temperature, and all other components except I constant. And this equation can be used to calculate the fugacity coefficient of a component in temperature. And that can be used by using, for instance, an equation of state. So what I have gone through here is just to define or establish a fundamental residual property relation. The starting point is the general equation connecting Gibbs free energy, volume pressure, entropy, and temperature. We make it dimensionless. We extend this to an open system. We state that we add some components, and then we add the amount of Gibbs free energy that is actually directly connected to the change in the amount. Then we just state that this is very general. Then we say that this is valid for an ideal gas because it is general. Then we have already defined the residual property as the difference between the actual property minus the ideal gas property. And then we get this fundamental equation for residual Gibbs free energy, which is 1155. If we also make use of the definition of the fugacity coefficient for a mixture, we can replace the last term with the sum of the logarithm to the fugacity coefficient of each component. And this is, say, just theory. And then to indicate that there is a direct application here, we can use this to say that the logarithm to the fugacity coefficient is the derivative of the residual Gibbs free energy with the amount. And then if we are interested in the fugacity coefficient for a component, and I am interested in that because that is a direct measure of the non-ideality of the component in the gas, and that can be calculated, for instance, by the use of an equation of state. That is the end of video 15.